At this point, we figured out how to write expressions for the position and the velocity as functions of time for objects undergoing simple harmonic motion. And so you might think that, hey, this could get put together with some of these energy types. Since we have kinetic energy that depends on velocity, if we have an expression of velocity as a function of time, then we could substitute that in and figure out the kinetic energy as a function of time. We could do the same thing with the position function and either gravitational potential or elastic potential energy. So when we combine those ideas, we have the equation for K, the kinetic energy here. We're just going to change the V to V as a function of T. And down here for US, so the potential energy in a spring, we'll change that x to x as a function of time. So typically these problems you'd be given the expressions for v of t and x of t, maybe mass and spring constant, and asked to write out equations for the kinetic energy as a function of time and the potential energy in the spring as a function of time. So that would look something like this. We've got our position as a function of time given, as well as our velocity as a function of time. Now we need equations for elastic potential energy and for kinetic energy. So elastic potential energy, US, that's 1/2 times k x squared. And then I'll just substitute in my expression for x, which is 0.5 times the sine of 0.25 t, and that whole thing gets squared. So now US is equal to, let's see, 0.5 squared would be 0.25 times 1/2 would be 0.125 times k, the spring constant, times the sine squared of 0.25 t. And when the whole sine function is squared, we usually put the squared right between the sine and the term that's being signed, just so that we don't think, do we do the squared first on this and then take the sine of that, or do we do the sine first and then take the square? This clears it up. So we do the sine of this number, and then we square that whole thing. So that's just a notation thing. So that's our expression for US. Now we're actually given the spring constant here, so we can go one step further. 0.125 times 3.125 newtons times the sine squared of 0.25 t. And so US then is going to be 0.125 times 3.125, and we get 0.391 times the sine squared of 0.25 t. And we can do the same thing with the kinetic energy and our velocity function. So kinetic energy, that's a capital K, is 1/2 mv squared. So here that'll be 1/2 times our mass. It's a big mass on this one, 50 kilograms. Times our velocity function, 0.125 cosine of 0.25 t. And that whole thing gets squared. So now we can rewrite that as k equals, let's see, 50 times 1/2 is 25 times the 0.125 squared. That'd be equal to 0.391. And then the cosine squared of 0.25 t. Alright, so we've got our first step here, our expressions for energy as a function of time. One depending on the sine squared of 0.25 t, one depending on the cosine squared of 0.25 t. The next part of this asks us to prove that the total Prove that the total energy does not change in time. Okay, so we need an expression for total energy now. Okay, so total energy, that would be equal to the spring energy plus the kinetic energy, which would be, let's see, 391 sine squared of 0.25 t plus 0.391 cosine squared of 0.25 t. And here's a neat little trick. We can factor out the 0.391 and we get sine squared of 0.25 t plus cosine squared of 0.25 t. Now, if it's been a while since you've had the trigonometric identities, then you might not remember this, but sine squared of anything plus cosine squared of the same thing is always equal to 1. So this whole middle term is just equal to 1. So our total energy is 0.391 joules times 1. That's it. This doesn't change in time, a constant 0.391 joules. Now we can actually do that in a more general sense back here. If we know that, say, our position as a function of time is equal to just some amplitude times the cosine of omega t, and then our velocity as a function of time would be the derivative with respect to time of this. Now, if you haven't taken calculus, don't worry about it. In fact, if you're not up to snuff on calculus yet, you don't need to do that for the AP test. I'm going to continue here. There's a little calculus. Watch it or not. If you're interested, watch the rest of this. So the derivative with respect to time of the position function, that'd be the velocity function. So the derivative of this is going to be a negative a omega times the sine of omega t. So then when we do our expression for kinetic energy, we'll have 1/2 m negative a omega sine omega t squared. So k is going to have a value of, 1/2 times n m times a squared times omega squared. That negative gets squared as well, so negative 1 squared is just positive 1, times the sine squared of omega t. And then us, the spring energy, is 1/2 times kx squared, which would be 1/2 times, it's a lowercase k, there we go, k times, and that was a cosine of omega t. And that gets squared, so us is going to be equal to 1/2 k a squared cosine squared of omega t. And then we'll pull in another equation here. We know that omega is equal to 2 pi f, 2 pi times the frequency, gives us our angular frequency. For a mass on a spring, we know that frequency is the inverse of the period, so frequency will be 1 divided by 2 pi times the square root of, let's see, for period it's the square root of m over k, so for frequency it'll be k over m. And so then omega, 2 pi times the frequency, would just be equal to the square root of k over m. So back up here, k now is going to be equal to 1/2 m a squared times omega squared, which would be just K over M times the sine squared of omega t. Okay, so our m's will cancel. We get a squared times k, just like we have a squared times k. So now our total energy is going to be equal to 1/2 times, no m there, times a squared k, the spring constant, times sine squared of omega t, plus 1/2, and I'll just reorder this one, a squared k cosine squared of omega t. So our total energy then is going to be, factor out 1/2 a squared k, and then we're left with sine squared of omega t plus cosine squared of omega t, which is just 1 again. So our total energy in the system is going to be 1/2 a squared times k. And this does not depend on time. It doesn't change over time. So from this we can see that the only thing that influences the total amount of energy in this system is going to be the amplitude of that system and the spring constant for that system.